This lesson deals with Supplemental Problem 9.3. You can find this problem in the course ebook in the Chapter 9 Supplemental Problems, starting on page 3. Given this circuit with two voltage sources, two ideal diodes, and two resistors, could you solve for the current in the diode D1 and the voltage across these two nodes? In part B, do the same problem but flip the values of the resistors. Our technique for solving ideal diode problems is to make a guess, and the best way to do that is to replace the ideal diode by a resistor. I'll call this RD1, and I'll call this one RD2, and the current will be defined from anode to cathode. I'm going to take a guess as to which way the current wants to flow. In most practical problems, the largest positive voltage has a current coming out of its plus terminal. In other words, it's generating power. The same is true if you think about this as a common point, that this is a negative voltage with respect to the same point as this one is, and it too would be generating power, the largest positive and the largest negative power supply. If that's the case, it would seem the current would want to come back this way, and the current would want to come back this way. I'm going to guess that RD1 is a short and RD2 is a short. Okay, now I'm going to solve for the current ID1 and ID2 in these short circuits and show that they're greater than or equal to 0. I'm going to call the voltage across this resistor V1 and the voltage across this resistor V2. If I go around this loop, the rise in voltage is 10 and the drop is equal to V1. So V1 is equal to 10. So this current is equal to 2 milliamps. That's not the diode current, but that's equal to ID1 plus ID2. Likewise, around this loop, go around the loop, the rise in voltage is 10 and the drop is equal to V2. So V2 is equal to 10 volts. So dividing that by 10K, I get 1 milliamp. Now that is my diode current, and it is greater than or equal to 0, so that checks. I can use that result to solve for ID1, back up here. So ID1 is going to be equal to 2 milliamps minus ID2 of 1 milliamp. So I get 1 milliamp, and that's also positive, so it checks. Lastly, I have to solve for the voltage V. Here, we just go around the loop. I've just got all short circuits. The rise in voltage equals the drops of 0. So it's equal to 0 volts. Now let's repeat the same problem by flipping the resistors. Using our same logic, I would expect the current to come out of this battery, and to come out of this battery, and then to go back this way, and to go back this way. So my guesses would still be the same. The diode 1 and diode 2 are shorts. Just erase these arrows. And now let's solve for the currents like we did last time. So the 10 volts here is really in parallel with this 10K resistor. It's not going to be 10 volts divided by 10K or 1 milliamp. And again, this current here has to equal ID1 plus ID2. The 10 volts here is across the 5K resistor. 10 volts divided by 5K is 2 milliamps, and that would be ID2. But now when we solve for ID1, it's going to be 1 milliamp minus 2 milliamps, and it's going to be a negative 1 milliamp. We get a contradiction with this diode. So even though we've got this technique for guessing, it does depend on the values of the components, is what I'm trying to show here. Let's try to change this guess and see if that improves it. So I'll make this an open with the current to 0. The 10 volts here is still across this resistor because of the short. In other words, the rise in voltage equals drops. And that current is also the current in diode 1, and so that checks for our positive value. And then we can go around the loop here and solve for D2. So the rise in voltage would equal the drop of VD2 plus 0 times 5K. That makes the voltage VD2 a positive value, greater than 0. In other words, 10 volts, and so that's a contradiction, so that can't be right. Let's reverse that. Let's put the short back here on diode 2 and then make diode 1 an open. Right now we'd have current flowing in this direction. So the rise in voltage of 10, would equal the drop of, say, V1 and V2. V1 is going to be the current, I sub D2 times 10K. And also that same current goes in the 5K resistor, so we get ID2 times 5K. We have 20 volts is equal to ID2 times 10K plus 5K. So now we can solve for ID2, be 20 volts divided by 15K, or 1.33 milliamps. So that checks. We can solve for the voltage VD1 by going around this loop over here. So the rise in voltage is 10. The drop is ID2 times 10K plus a drop of VD1. ID2 is 1.33 milliamps. Multiplying that by 10K, you get 13.3 volts. And subtracting that from 10, you get a negative voltage. So that's less than or equal to 0, so that checks. And then lastly, the current in this open circuit is going to be 0, and that's the other variable we're going to solve for. And the voltage V is the voltage across diode 1, which we found to be minus 3.3 volts. And this is an example of ideal diodes where the value of the resistance does determine the direction of current.